Water is the most valuable resource on the planet. We do not value it as highly as we should. Maybe that's because we see it everywhere and view it as an unlimited resource. But maybe if we faced serious droughts or could not access safe water like billions of people around the world, we would see its inherent value and why we need to treat this resource adequately. Water stresses are starting to become more prevalent. We can see this in areas that have previously not had stresses before, like the southeast of England, which is expected to face serious droughts in the coming years. Due to these new issues, the government is developing new strategies to tackle these stresses from increased population and the effects of climate change. Our water network has evolved throughout history, offering fantastic benefits, but also having some environmental impacts through this approach. Through this programme, I want to show you how the system has evolved and how we can look to having a new decentralised system that embraces the circular economy to extract the valuable elements in wastewater so that we can overcome future environmental challenges that we will face. Throughout history, major settlements and towns were formed around natural water resources. As societies developed, we could move further afield, with our ability to transport water from its source to the communities and transport wastewater away. Typically, wastewater was discharged into rivers and oceans so it could be suitably dispersed into the water source. The Greeks and Romans were the first to implement indoor plumbing and water transportation through aqueducts. The idea of reusing wastewater was implemented years ago. In Japan and China, they used it as fertiliser as there was a lack of cattle manure. In Europe, we used it to produce potassium nitrate, also known as saltpeter, so that we could produce gunpowder. Things changed as resources became more readily available, and we started to see wastewater as something we wanted to distance ourselves from, which led to us not reusing the waste and disposing of it in a linear approach. As cities started to grow, the way we dealt with wastewater was inadequate. This led to overpolluted streets, which acted as a constant source of disease outbreaks. Wastewater was typically dumped into local resources. The River Thames suffered heavily because of this. In the 18th and 19th century, Londoners and local industries, as they expanded, used it as a communal dumping ground. The situation got so bad that the chemical reactions taking place from all the chemicals that the industry applied in actually started to increase the temperature of the water, and there was such a foul stench that people needed to know that there was something going to be acted on. This led to the city's sewage network being constructed by engineer Joseph Balzagat to stop waste entering the Thames. This sewage network has been the foundation of our current system, with many pipes still in use today. As our population has grown, this has put pressure on the system that is unable to keep up with the ever-growing amount of wastewater. The original system was not designed to cope with the vast population we have now, and the additional rainwater and surface water that enters the sewage system from the new developments and roads that we've built that stops it from entering the ground. Rainwater adds complications. From the added pressure it puts on the water treatment works to clean the additional flow, it also dilutes the waste and collects heavy metals and other contaminants that are found on the road surface. Sewage systems need to be able to discharge waste quickly during heavy rainfall to stop flooding or disease outbreaks. Recently we saw that in London, the Thames had billions of litres of water dumped into it from the sewage system. This could have a negative environmental impact on the water quality, especially as it was proclaimed dead in the 1950s due to the heavy amount of water sewage that was there. And now we're only just starting to see life come back into the Thames. If too much sewage or organic matter enters water sources, it can remove all the oxygen in the water that sustains aquatic life. If this happens, then the water source is proclaimed dead. The oxygen is removed due to the reactions that take place to break down the waste, which produces water and carbon dioxide. Water sources are able to break down small amounts of organic waste that is dumped into them. However, the vast volumes that we produce is not sustainable, and this will affect the biodiversity. This is why we have to treat the waste before we dump anything or discharge any water back into the environment.
The typical treatment process works in a linear approach. Once the waste reaches the treatment plant, it goes through a screening process to remove what should not have been down the drain, such as nappies, face wipes, sanitary items and cotton buds, which can result in major blockages, as we recently saw with the 250 metre long fatbird blocking the sewer. The primary treatment stage removes the human waste from the water through large settling tanks, where the solids settle at the bottom so the sludge can be removed. The water goes through a second stage treatment, which pumps air through the water. This is the most energy intensive part of the treatment process. This stage encourages the good bacteria to consume the contaminants left and remove the nitrogen and phosphorus from the water. The water may then be passed through a sand filter before it is returned to the water sources. The sludge that has been extracted can be reused for other resources, such as agriculture or to produce energy.
The main problem with centralised systems comes from the different variety of waste streams that we have that are added together and then diluted with surface water. When we come to treat the waste, this means that chemicals are in very diluted form, and also if we're going to extract the waste, it makes it more difficult. If we look at the different waste streams that we have coming from our house, then we can understand how much more complexity this adds on a much grander scale.
We have chemical waste from dishwashers and washing machines, which also contain microfibers and plastics, food waste from our sinks, and human waste from the toilets. Then we have all the water from the showers and the baths added in. Already we have created a complex chemical concoction. The water from our households is then mixed with rainwater that enters the sewage system. All of these waste streams require different types of treatment or have a resale value. We need to start thinking of ways to recover, reuse and treat the waste streams locally before everything is mixed together.
This can make it a lot easier and more sustainable to extract these elements than a centralised system. To understand the benefits that a new approach could have, we need to actually understand the relationships that water has. And we can see this through the energy, water, food nexus.
All three of these elements are essential to our way of life and are intrinsically linked. We can see this as water is used for irrigation to grow crops, and water can be transported virtually through the embodied water it takes to grow crops. Virtual water trading can also allow areas under water stresses to import goods with high water demand from areas with an abundance of water. Agriculture can produce energy through crops, or agricultural waste can be used to produce energy. We require energy to grow crops from the machinery that we use to plough the land and to transport it to our tables. Energy is required to carry out water treatment processes and pump water to our homes. And energy requires water for cooling.
These relationships can help us understand the role of water in our society and the potential benefits a decentralised system could have. If we look at what makes up wastewater and what can be extracted, we can see there is an abundance of energy and nutrients, along with the water that can be reused locally.
From this, we can see that wastewater can play an essential role in the nexus, sitting in the centre and supplying elements to all three aspects. The nutrients found in wastewater are nitrogen, phosphorus and potassium. These are vital for crop growth and our agricultural industry, as they make up the fertilisers used around the world. In water, they can be detrimental to the ecosystem, as high levels of nutrients can cause algal blooms. When the algae die, it drops to the bottom of the water, which then uses up the oxygen to break it down, causing dead zones. Some nutrients, like phosphorus, are also limited resource and are currently mined.
Urine contains the most nutrients in human waste. If we collected urine from 4 people for a whole year, we could produce 50 kilograms of fertiliser. So if we look at extracting the urine before it's mixed in with these other sources, we can then reduce the amount of energy that is used to remove those nutrients at the treatment plants, and we can reduce the amount of energy that is used to produce fertilisers. EWAG Aquatic Research Centre in Switzerland has demonstrated at 2 sites a decentralised urine treatment system. They have then started to produce a fertiliser which they are now selling, and this model is commercially viable. Another issue that is becoming more prevalent is the build-up of pharmaceuticals and chemicals in our natural water systems. This is because we're unable to process and just remove all of these chemicals because they're in such diluted forms. In many cases, they're not actually having an effect on the environment, but we have seen that near discharge points that there is a high level of estrogen that's actually changing fish from male to female. And in a lot of cases with pharmaceuticals, we don't actually know how they interact together because we've never done that testing. So in this case, we need to start thinking and taking the precautionary principle. We don't really want to find out the actual effects it can have, so we need to start looking at ways of removing these chemicals when they're in high concentrations. And predominantly pharmaceuticals are mainly found in our urine, and chemicals, we can look at ways of removing them when they're in high concentration.
One way to do that is to look at where chemicals are added, such as detergents used in washing machines and dishwashers. We can easily treat these through an ozone or UV treatment system before the water is mixed with other resources, as the chemicals are in the high concentration. Another option could be to look at recirculating the chemicals in the water through multiple cycles with small additional top-ups as the chemicals do break down.
There are a lot of emerging technologies that allow us to recover the potential energy within wastewater. Now, this potential energy doesn't come from the water itself, it comes from the organic compounds and the contaminants within the water. So we need to look at the waste streams that have the higher solids and the higher potential energy and just try and stop them being diluted with other sources.
So taking the high solid waste streams that aren't mixed can aid in this process.
The most established energy recovery technology for wastewater is anaerobic digestion. This breaks down the waste with bacteria and a lack of oxygen. The bacteria break down the organic compounds. As they do this, they can produce CO2 but also methane, which we can then use to recover to produce energy. Another technology is pyrolysis, which heats the waste up to high temperatures so that we can produce gas, biochar and oils. Gasification goes a stage further, increasing the temperature so that the biochar and the oils that are produced are then also turned into gas. These technologies can range from small scale to large scale. And however, anaerobic digestion is the one that's most commercially available at a smaller scale currently, but there are plans and companies are working on developing new pyrolysis and gasification systems that can work to treat sludge and household waste at a small scale. Another technology is also biological electrochemical systems. These systems use bacteria and electrochemical processes to break down the waste. And this allows us to produce electricity, methane, hydrogen, and other value-added chemicals that we can reuse.
So, in an ideal system, in a new housing development, we could use rainwater collection for either flushing or gardening. A grey water system could be integrated, which cleans the water from the sinks, showers and baths to be reused to flush our toilets through a filtration and ozone or UV treatment. The wastewater can then be collected from the households into a settling tank where the sludge can go into an anaerobic digester, which can produce methane. This methane can power a combined power heat unit that can then provide electricity and heat to the households. The digester can be collected by local farmers or used by gardeners due to its high nutrient content. The water can go through different filtration stages to remove any contaminants, and then go through a final UV treatment stage. This water can then be sent back to the households, creating a closed loop system.
We can start implementing some of these aspects now into our households, new developments or skyscrapers or large commercial buildings. I don't see decentralised systems completely replacing the centralised model that we have now, as they're really good at dealing with large volumes of water. However, we need to look at extracting the valuable elements before it goes to that stage, So it makes the decentralized system easier to work with, so that you have less strain on the chemicals and energy demands trying to remove the organic compounds. And as we are seeing now with the energy sector, more decentralized systems popping up with people using solar or wind to generate, I believe that wastewater and water treatment systems can also take this approach. A current project I'm working on is developing decentralised wastewater treatment systems for Ugandan refugee camps in partnerships with Mercy Corps. The project aim is to test out different technologies to look at the energy recovery potential, but also recovering the nutrients and the water that can be reused for irrigation. The project wants to look at the social, economic and the environmental aspects of each technology and the acceptability of the project in total. Ultimately, we want the project to be commercially viable so we can offer entrepreneurship opportunities and jobs for the refugees in the future.
The first system will be for households using low-cost microbial fuel cells. The microbial fuel cells have two sides. On one side you have the carbon anode. You grow bacteria on the anode that forms a small biofilm over the surface. The different types of bacteria in the biofilm work together to break down the organic compounds in wastewater. As they do this, they transfer electrons to the anode, which passes through a circuit producing electricity as the electrons go through to the cathode, to combine with hydrogen and oxygen to produce water. We will use the small amounts of electricity produced to power light bulbs for the households, with the treated water being used for irrigation on their small holdings or to increase crop yields. The second system will be for larger communal areas. They will use a microbial electrolysis cell that work in a similar way but have an additional electrical charge supplied. We are looking to power this through solar panels. The system requires a small amount of electricity so that additional energy can be used for other purposes depending on the local needs. The additional electricity means that we can then start producing hydrogen and methane at the cathode. This can then be stored and be used for cooking, supplying restaurants or local homes.
The main aim of this project is to offer alternative solutions to pit latrines, which require costly desludging and regularly overflow during heavy rainfall spreading disease. Through our circular economy approach, we want to improve the health benefits from the improved sanitation, offer a sustainable energy source and increase crop yields from the nutrients and fertilisers that we can produce. But ultimately, if we're successful, we'd like to roll out this to other communities and underserved communities and build the foundations for a decentralised water system that eventually we can build on and increase and to improve the benefits that it could have.
These are just some of the ways that we can think of reusing and treating wastewater. There are some exciting technologies and approaches being implemented around the world to tackle one of the biggest environmental challenges of keeping our water clean.